we are going to subject with respect to all these axial force. I'm taking as a comparison one sample case and shear forces and then torsional moment and bending moment for both axes also. You know, right, what is x direction torsion and what is this
Yeah.
major axis
Hmm.
bending and minor axis bending and vertical shear and horizontal shear, then
Yeah.
axial loading also. You know, all those 6 degrees of forces, right?
Yeah.
Okay. So once we take this tubular and apply all these forces, whether this member is passing or failing, that's a thing we are going to find it out. So we are using APRP2A method. Okay.
Hmm.
And this Young's modulus for the steel and yield stress also for
Property.
the
Yeah.
steel. And reduction factor, it is the moment reduction factor, it will come as per APRP2A. This we will explain. And load factor, this is for LRFD, but now we are doing ASD. We
Hmm.
will see this working stress method. This inner diameter, you know how to calculate diameter minus 2 times thickness. Cross sectional area also by square before you can get it.
Hmm.
Shear area, this shear area is important for calculating the actual shear stress. You know, in the circular shape tubulars, the shear area is only 50 percentage of the cross sectional area. Okay, 50 percentage of cross sectional area we need to consider for the uh, shear stress, actual shear stress calculation. Okay, this also you can see it in the APRP2. I will show you. The moment of inertia, you may be knowing how to calculate special the materials, and polar amount of inertia is nothing but summation of both axis amount of inertia, and section modulus is nothing but I divided by maximum fiber distance, and plastic section modulus also we can get it. Shape factor is ZP by Z. It's plastic section modulus divided by elastic section modulus. Radius of gyration, these are all geometrical property, you know. Slenderness ratio
Yeah.
also we need to calculate. That's mainly for calculating the allowable compressive stress. This is important for the slenderness
Hmm.
ratio. So check for tension. Allowable tensile stress is we are taking 207. How means we are using the APRP2A. It is saying, see here, if you go to this APRP2A allowable axial tension,
Hmm.
it is zero
Point
point
six.
0.6
Yeah.
times Fy. So allowable tensile stress for cylindrical members, it says that subject to axial tensile loads should be determined from zero point 0.6 Fy. If it is tensile load, if it is here you see Fy is nothing but a yield value of the material. If it is
Hmm.
compressive stress, it depends on different factors. You see,
Point
axial
eight.
compression depends on the
Hmm.
should be determined from the following equations. It depends on the d by t ratio,
Hmm.
and also if it is less than 60, we are following like this, and if it is greater than 60, then we need to consider the local buckling stresses also instead of
Hmm.
Fy value. Instead of Fy yield value, we need to consider FXE or FXE. Now, that is nothing but critical local buckling stress. That and all we will tell you when we go to this API sections. Okay, and this is nothing but some program what we are doing it in Excel, so we can use easily calculate the allowable stress. So I will tell you this also how we are doing it in the Excel sheet. Okay, so this you know now how this 207 is coming. That's nothing but from APRP to 8.6 times Fy it would come. The maximum tensile stress, if you see, that's nothing but the tensile force divided by cross sectional area. It
Hmm.
would come. Okay. And the UC ratio is nothing but what's the actual stress divided by allowable stress.
Hmm.
So that's the one. If it is less than one, it seems the member has more capacity compared to the actual load what it's going to experience. Okay. And check for compression. This it comes 190 only. How it comes? That's what we were explaining here. If you see, this is bending stress. This is the axial stress. It depends on diameter, thickness, K factor, yield strength, Young's modulus, and this one is nothing but allowable stress. What we are doing it.
It's not depending on the length itself because of the
No,
cylinderness.
it depends on the length. That is a factor K. I'm telling
Ah.
right. K. If
Ah.
you see
Okay.
here somewhere, it would come like K by
KL
C. It
overall.
is
Yeah.
yes. It depends on the length of the member. Definitely, the
Hmm.
length of the member it comes in place.
Hmm.
You see here allowable compressive strength. You see KL by R squared is there, right? Here this L is the unsupported length,
Okay.
unbraced length. So K is the effective length factor. L is the length of that member, R is the radius of gyration,
Radius.
KL
Mhm.
by R is the factor called the slenderness ratio. If slenderness ratio increases, your allowable stress comes
It will
down.
be less, yeah,
Yes, that's the compression
because it will increase the
value.
buckling, yeah.
Yes, and you see this scale by R squared 2 cc squared. Cc is nothing but 2 pi squared E by Fy. Square root of this values and all used for calculating the allowable axial stress. Okay.
Mhm.
See here, E is the Young's modulus, K is the effective length factor. This we will see how we are calculating the effective length factor in the subsequent section. And R is the radius of gyration. When members having dBT ratio greater than 60, we need to substitute the critical buckling stress FXE FRE for FY instead of in determining CC and FA. When we are determining the CC value and FA value, we need to use FXE or FXC instead of FY. Okay, here you see FY is the right.
Yeah,
In this place, we need to use FXE or FXE, whichever is smaller. Okay.
okay.
You should know like what do you mean by FXE or FXC. FXE is nothing but elastic local buckling stress. FXC is nothing but inelastic local buckling stress. So elastic local buckling stress also depends on thickness and diameter. If it is local buckling, always it happens if the diameter by thickness ratio, if it is
More
greater
than.
than 60.
Mhm.
Right? If it is like a diameter is very big and very small thickness, then it
Yeah,
can locally it can buckle. If you see this member, it may be local buckling can happen
yeah.
when the load is increasing for the compressive loads. So here this it depends on diameter, thickness, and Young's small this E value, that's Young's smallest. And then C. C is nothing but critical elastic buckling coefficient. This is very important. C is the critical buckling, elastic buckling coefficient. This value depends on theoretical value is 0.6. However, reduced value 0.3 is recommended for the use of equation in this equation 6.4 to account for the effect of initial geometric imperfections within the API to be tolerance limits. There is one code called API2B. API2B is nothing but for fabricating the tubulars. We are using it fabrication of steel tubular fabrication. There will be some geometric imperfections. All these things it will be there. It will give the tolerance limit also. If you are within the tolerance limit, then we can use this C value of zero point 0.3. If you use zero point 0.3, what would happen? FXE will be less. If you are using zero point 0.6, FXE will be more. If this FXE is more, your allowable stress also it would go up because it depends on this. It is directly proportional to Fy, right?
Mhm.
Allowables is directly proportional to Fy. If it is directly proportional to Fxc, then your allowables would increase. So if C is increasing, this critical elastic buckling coefficient, you will get more FXC. That in terms of allowable more compressive stress. So its recommended is zero point 0.3. So we would be using zero point 0.3. We can use it instead of theoretical value. And you see inelastic local buckling stress. You need to calculate both elastic local buckling stress as well as inelastic local buckling
Mhm.
stress. Whichever is less, that we have to use in place of Fy. This inelastic local buckling stress also it depends on the diameter by
Diameter,
thickness.
yeah.
This ratio 1.64 minus 0.23. If it is less than or equal to 60, we are directly taking Fy. It's always it's okay. If it is more than dBT is more than 60, then only we are going for this value. And we have to see like a FXC, if it increases more, then we should limit to elastic local buckling stress. That's what here it is saying.
Mhm.
Unstiffened cylindrical members fabricated from steel should be investigated for local buckling due to axial compression when dBT ratio is greater than 60. So whenever the dBT ratio is greater than 60, we need to uh, investigate for the local buckling. And if the dBT ratio is greater than 60 and less than 300 and wall thickness greater than 6 mm, both elastic as well as inelastic local buckling stress due to axial compression should be determined from equation
Mhm.
6.4 and 6.5. These two are it's given here. There are conditions. What are the conditions? It should be more than 60 and dBT should be less than 300. If it goes more than 300, then there is something called APA2U. There is one more code. It is there that we need to follow for calculating the elastic and inelastic local buckling stresses. Okay. And the wall thickness also should be more than 6 mm. Mostly we don't go with like a very small wall thickness because it can buckle very easily locally. That's why
Mhm.
we don't go like this kind of things. Usually company also specifies dBT ratio should be less than 60, like that it would come in the specification itself, company specifications when we are selecting the materials. Usually we go for dBT less than 60 so we can avoid all these local buckling issues. like elastic local buckling or inelastic local buckling, no need to calculate, and to place it instead of fy, to replace fy with f xe and f xe. That we won't do it as long as we keep dbt less than 60. Okay, because
Mhm.
dbt less than 60 means we can avoid all these local buckling issues, and then we will see bending also. So here, this is how we are calculating the allowable compressive stress. Then actual compressive stress, load divided by area. That's the same 39.1. UC ratio is nothing but this ratio, this actual stress divided by allowable stress. If it's less than 1, it seems the member is safe.
Mhm.
Euler elastic, allowable Euler stress. This value only that here we have seen right in the APA, FE dash. And maximum compressive stress is, that value is this same, and UC ratio is this value. We are comparing with allowable Euler stress as well as actual uh, compressive stress. Okay, this allowable compressive stress, this is allowable Euler stress.
So Euler, it's for the axial force for the
Yeah,
pile itself, because
yeah, yeah,
I think we use the same thing for the
yeah.
column.
Yes, but
Yeah.
usually we will be checking for this allowable axial stress mainly. Okay, and for UC, for KL by R, if it is
Yeah.
less than CC value, 12 pi squared E by 23 by KL by R squared. If it is more than this is, sorry, this is for this, okay.
Yeah.
If
Yeah.
it is less than this, we are going for like this. If it is more than CC value, then we are taking 12 pi squared E by 23 KL by R squared. This does not depend on the yield value. You see here, there is a difference between this FA and this FA. Do you
Yeah.
understand?
Yeah.
One minute, let me clear this. So it will be easy to understand. See, there is a difference between this value, this FA and this FA. This FA mainly depends on the yield value,
Yield.
but this FA does not depends on yield value. It depends only on the Young's modulus and then KL by R ratio. That means slenderness ratio and Young's modulus. When
Mhm.
KL by R is higher KL by R, that is CC value is more than KL by R is more than this CC value. Okay. So in that case, that's what we are checking it here. See here, 12 pi squared E by 23 KLR squared. A mode is for allowable stress modifier. If it is extreme loads, we will be considering that. I would say it separately. But this value, this is the Euler allowable Euler stress. This value also we need to check in case if the CC value is KL by R is higher than CC value. Understand, right?
Yeah.
So that allowable Euler stress also we need to check it. So here, if the axial stress, you see d/bt ratio diameter fxe, that zero 0.6 into e dt, and fxe is this 1.64.23 d/t. That is, these values are here. It's given 1.64.23 and 2 cet. These values and all we are putting it in the VB macro. So we will see first d/t is less than or equal to 60. Then yield value we can take as fy1 value itself. If fxe is less than xe, then we will take fxe itself. Else we need to say yield value is fxe. This is what the condition given here, right? This is the condition. This condition and this condition. So that condition we are putting it in the VB macro. So we can take the allowable accesses. And if you see, like first we need to calculate the CC value, 2 pi squared by E and Fy square root of this value C. And Kc we are calculating K by C, this ratio. And then if you start case, if it is slenderness, K is nothing but KL by R value only. If this slenderness value is less than CC, then we need to use yield value. Also, it's a function of allowable stress outcome. If it is more than CC, that yield value is not at all function. That's what I tried to tell you.
Mhm.
Then this is LRFT value that we are not using it for this one. Usually we are using it WST 2007 only. So here you see this KC squared, and this is nothing but the your slenderness ratio. That's what here we are using it, right? KL by R whole square. K is nothing but KL by R. Okay, this K,
Mm-hmm.
KC value. Okay, this is for the bending. See, allowable bending stress. Allowable bending stress, how we are calculating, we will show you here. Allowable bending stress is,
0.8.
see, allowable bending stress also
Okay.
depends on the d by t
And the
value.
diameter, yeah.
Yeah, if diameter by thickness value is less than this number 1030340 by FI in SI
Mhm.
unit, then MPa you have to put this also MPa. Then you can take directly 0.75 FI. If diameter by thickness ratio varies between this value and this value, so suppose FI is 350. In our case, if we are considering 350, 10,340 divided by 350, if we consider how much it would come, it would come 10,340 divided by 350. It's coming as 29.5. 29.5. So if diameter by thickness ratio, say if it is 610 by 25.4, we consider right in this example. So it becomes like a 24. So we can directly use
Yeah.
0.75 FI. If diameter is, suppose if thickness is only 10, then what would happen? It would be d by t, it will become 61. 61 means it may come in between this ratio 20680 divided by 20680 divided by 350 is nothing but 59. So this formula also we cannot use because it's 61. Then we need to use this formula
Mm-hmm.
1005, sorry, here 206080 less than 300. Then it will become 0.72 minus 0.58 yield value, diameter, length smallness, then thickness. If you put this value, then FB we can get it in terms of FY. This may, it may come even zero point 0.5 times also it can come. So it always depends on the ability ratio, the allowable bending stress also. Okay. So we should not simply take 0.755. We need to consider the debate ratio in which factor it's coming, like which range it's coming. So based on that ratio, we need to use this formula to calculate the allowable bending stress. Okay. If debate ratio is greater than 300 mm, 300 not mm, 300 ratio, then it becomes API to U. That shall be used. Okay. So here, if you see, this is what I was trying to tell, like allowable stress we are calculating like this. And formula also, if you see here, we are putting it in the we be like this diameter, thickness, Fy value, then this smallest value also, the stress value also, young smallest, and this WST or LRFT, like that we put this factor.
Mm-hmm.
dt is the d by t we can write. X is nothing but Fy into d divided by et. This one value we are simply calculating the x value. Then we can compare that with the d by t with this factor. If it is d by t less than this value, we are taking directly 0.75. If it's between this and this, we are taking this 0.84, 1.74 into x. X is nothing but we have seen here, right? Fy dt et. This value we simply calculated x and stored it 1.84 minus 1.74 into x. So 1.74 it will come here. If it is debating between this ratio and this less than 300, we can take 0.58x 0.72 in yield value. If it is greater than 300, then we are telling that use refer API plugin to you. Okay. This is if you are using with allowable stress with the APRP to AWST. If it is LRFT, then it would have the different factor 0.9 by 1.13, but we are not using this Excel sheet for mostly LRFT. We are using WST. So this value you can this is the right. This kind of small function we are putting it in the VB macro. This function is to calculate the bending stress. Okay.
Mm-hmm.
So with this we can calculate the bending stress also. Then maximum bending stress. This actual bending stress we can calculate M by Z value. Then UC ratio we can calculate actual divided by allowable. So
Mm-hmm.
if this would be less than 1, it's okay. This is uh, FBY bending. This is FEZ bending. There are two bendings are there. So
Mm-hmm.
both we can check it. Allowable shear. This one is also 138 is calculated. How you means allowable shear here you can see beam shear for the lateral loads force divided by 0.5 times A. So it's a maximum shear stress. B is the transverse force, that Fy value on force in y direction, force is the direction we calculated, right? A is the cross sectional area, so we are considering 0.5 A as per this actual bending stress. Allowable bending stress is nothing but 0.4 times Fy. Allowable beam shear stress would be determined from 0.4 times yield value. 40% of yield value is taken as the allowable shear stress. While the shear yield stress of structural steel has been variously estimated as between 50% to 5 by 8 of the tension compression yield, frequently taken as 1 divided by square root of 3. 1 divided by square root of 3 is almost 0.577, almost 60, 57, 58 percentage. Its permissible working stress values given in AAC, two-third of the recommended, as the two-third recommended the basic allowable tensile stress. If you see this one, two-third of recommended basic allowable tensile, basic allowable tensile is 0.6, right? 0.6
Yeah.
into 2 divided by 3, if you see it is 0.4, it comes.
Okay.
So two-third of allowable tensile. Allowable tensile is 0.6 Fy. So two-third of 0.6 Fy is nothing but 0.4 Fy. That's what it's recommended.
Mhm.
Its permissible working stress value is given by AAC, a two-third of recommended basic allowable tenses. For cylindrical members, when local shear deformations may be substantial due to cylinder geometry, reduced yield stress may need to be substituted for Fy in equation 6.1. That's a different equation we will see it here. Allowable torsional shear stress, it's coming, right? 0.4 Fy for torsional also we are considering it. They are telling that based on the cylinder geometry, we may need to consider the reduced yield value also. Further treatment of the subject appears in reference work statement. This is the API value. This we will see it in later stage. But you can say that for allowable shear stress we can take 0.4 Fy. Actual shear stress we can take 0.5 times A. That's the cross section area. Taking from load shear load divided by 0.5 A. That's how we can take in the allowable shear stress. That how we consider in the here you see the here we are taking allowable shear stress simply 0.4 Fy. So 0.4 times Fy 138. That's why it's simply taken here. And resulting shear, this is the Fy squared and Fez squared. This is the actual force. So maximum shear stress is there is a combined resultant shear is 9.69 shear stress. So 9.69 divided by 138, we will get 0.07. And check for torsional shear. You know this torsional shear, my actual torsional shear stress is nothing but torsional moment divided by polar moment of inertia divided by the extreme fiber stress, it will come. So 0.22 divided by this is also 0.4 Fy we have seen, right? That's how we can take the we will check like how much it is, whether it is less than 1 or not. And check for combined axial tension and bending. This one you see it is applicable only. Fa we know, and 0.6 Fy also we know. Fbx, Fby we have calculated already. You see here. Tensile stress we know 39. Bending also we know Fby, Fbz. If we substitute all this value and we have to see it's less than 1. The combined tensile plus bending. The same way combined axial compression bending also Fa we know that's the actual compressive stress that we have calculated here 39.39. And Fa, this is the allowable compressive stress that we have calculated here. See 190 point something it's coming. So you can put this value and the Cm is a 0.85 and Fbx squared, Fby squared is a bending stress. 1 divided by this is Fa is the actual and Fe dash also we calculated the compressive stress Fb. This is the allowable bending stress. This would be less than 1. This also these three factors are given in the APRP2A that I will show you. That's what exactly here it is given here. Combined loading, if you see all this value we need to calculate y value k by Fy by E, Fe equal to 0.85, Fy y squared. This is the
For
FB
the
compression.
point,
This is coming from here. I will show you here.
for the point 85, the reduction factor, why
Yeah,
it's fixed? Is it because the end point for our member it will be fixed? That's why it's 0.85, the reduction
One,
factor, CM.
no, no, 1 minute. I will show you why we are taking this one. Why? That is because of imperfections and error come. You see here. Cylindrical number subject to combined axial, combined compression flexure shall be proposed to satisfy both the following requirements at following along at all points along their length. CM value is at 0.85 we are taking, right? That because of the imperfections and all we will be taking the moment reduction factor is there. You see here. I want to show you where it is taken. This one will drag and inertia coefficients it's coming. Moment reduction factor is there. Yeah. Moment reduction factor only is based on the end moment conditions. This I will tell you like where exactly we can take these references of CM, why we are taking this as a less value like that. Okay. Tubular members under axial compression are subject to failure either due to material yield or Euler buckling or local buckling. Mainly yield or buckling is the failure criteria it would come. For design against Euler column buckling, use of AIC factor. If you go to AIC, it would give this moment reduction factors and all. However, to supplement this one, interaction equations for the cylindrical number and the axial compression and bending together with recommended values for effective length factors, moment reduction factors. Okay, this effective length factor, based on the end conditions, whether it's fixed or fixed pinned, all
Yeah.
these things. Moment reduction factor also based on the end moments. Okay, because it's the
Okay.
interaction between the bending as well as axial together it comes, right?
Hmm.
Both axial as well as
Yeah, yeah,
bending.
yeah. It's
So
clear.
that moment reduction
Because
factors we need to put it. If you don't
I
put this CM value, if you don't include it, how
I
much it would
mixed
come?
between them the K factor and CM factor.
No, no, no. These two are
Yeah,
different.
yeah.
Yeah.
On them depending on
Yeah.
the
K is
end
the
of the
effective
member.
length.
Yeah,
Yeah. This is depends on the uh
yeah. If it's fixed
fixity.
or yeah,
Yes.
swaying. Yeah.
Correct. Yes, I will show you somewhere here.
I think there is as a graph to how to choose the K value from the chart,
Yeah, yeah.
depending on
There
the
is
end
the
member. Yeah.
yeah,
Is
see
it
here.
sway or non-sway? Yeah.
Yeah, yeah. This is the one. Values of K and CM for various member situations.
Mhm.
You see superstructure legs, braced or portal. Unbraced, we are taking K value we need to
Yeah,
calculate.
braced and
Braced is
braced.
we
Yeah.
are taking 1, 6.3.2.5. That's a CM factor telling, right? We 6.3.25. Yeah, this is the one. This is what I
Yeah.
was trying to refer.
Yeah,
Values
depending
of
on
the
the
reduction
moment. Yeah.
factor CM refer to table 6.1 with terms as follows: 0.85, 0.6, 0.4, M1, M2. These are the n moments, but not less than 0.4, not more than 0.85. It should not go more than 0.85, but it should not go less
Mhm.
than 0.04 also. Next is 1.4. This is FA. FA is the compressive
Yeah,
stress. That
compress.
one. This is the buckling Euler stress based on that factor, but it's not go less than point. See, point. It's not go more than 0.85.
Yeah.
Here also, whichever is less, we need to consider. That's what we have to consider for the allowable combined interaction between the axial as well as bending. You see, here this is the one I was trying to tell in the Excel sheet what we are putting it. If the actual compress is allowable compress is less than 0.1, 15 percentage. If it is only loaded 15 percentage, we can take the equation 6.22. We can use it instead of 6.2021. See here, these two value we
Mhm.
can avoid it if only the 15 percentage
Yeah.
actual compressive stress is only 15 percentage allowable stress. We can simply take FA by FA, FB x square, FB y square be FB. That is here. But here, if you see the more interaction terms, it will come. FE dash also we need to calculate, but here it is that it will not come because if the only 15% only it's loaded in the axial, remaining under bending only means we can take this factor. Equation 6.20 assumes that the same value of CM and FE dash are appropriate for FBX, FBY. If different values are applicable or based on either other rational analysis would be used instead of this equation. We can take CMX and CMY different directions. Okay,
Okay.
because moments in different directions may be varying. Okay,
Okay, I got it now.
so this is what here we are using in this Excel sheet, like with the different combinations. We need to consider all these three equations. We need to put it. So that's what it was done here.
Okay.
So this is the combined axial compression bending. Once we check combined stress also, if it is less than one, then that member is able to take whatever the forces it is being subjected to.
Mhm.
And so in the Excel sheet also how we are considering it. See here, this diameter, thickness, length we are giving it, and this is what I was trying to tell. All over stress 0.6 Fy we are taking
Mhm.
it. If it is ASD 0.6 Fy, otherwise if it is LRFT 0.95 Fy, that is LRFT factor that would come. It's not 0.95 Fy directly it will come. So we are taking only ASD only.
Mhm.
This UC ratio means nothing but actual divided by allowable. This is the actual
Mhm.
tensile stress. Actual tensile stress is nothing but what is the force divided by cross sectional area. This load factor it's one only. So it's actual tensile stress. Actual compressive stress also same way because we are taking the compression force is same. And allowable value only we are taking this F axial. This is the function what I was trying to explain. This function I was trying to tell you, right? If you see here, this is the function for axial. It depends on diameter, thickness, K value. So here, if you see this K value and all, we told right like KL by R based on that it will come CC value. K value here in this Excel sheet you can calculate. Okay, this Euler buckling stress. This is what I was trying to explain to you. And if you go to Sachs, one simple model I will make. Okay, then you can understand. So once you open Sachs, go to the modeler, create new model. Start blanket model. I'll set metric clonate force. I'll make one joint, add, and I'll put this as a um, cantilever. I'll put it. Okay. So first joint and fixity, I'll put it fixed at the cantilever end and joint. I will add one relative from here, 5.6 meter length, right? In next direction, I'll put 5.6 meter length. Apply. So here it comes. So I will add one member also. Member add from here to here. Then I'll put that the tubular one. For this, I need to give the properties also. Member property. What I will do? What is the diameter? Diameter. It's not general. It's a tubular.
Tubular.
Diameter 610 and wall thickness 2.54. Smallness. Okay. Yield value I'll put 34.5. Density I'll put 7.89. I'll put apply. So I have defined the tubular. If I click this one, you can see this is the tubular line. So I will save the file, save as both model and C state. Okay, I'll go to this one, some right design basis. I'll put the new folder. Tubular member. Tubular member. Okay, so I created only the geometry and all these things, and load I have not yet defined. So what I will put, I'll put load in each case. I'll put all the 6 degrees of freedom loads at one point. If I put load here, it will automatically add additional moments and all. Right. If I put this one because fixity I have given here, whatever the force I am applying it, it will give additional bending and all, right? And it will give the shear stress also. So one
Yeah.
simple case we will do it, not exactly the same Excel sheet. We will put one simple vertical shear and one axial also I'll put it without any torsion. It will create one bending on the major MY axis, and lateral load we will not consider. Only one vertical load if you put, it will create one MY bending and vertical shear, and one axial also we can put it. So three forces I am going to put. So at this joint, what I'm going to put, one axial and one vertical. That's enough. I think load condition, I'll put force. This also force, I'll put it simple force. So force, what I'm going to add in vertical direction, FZ. FZ minus, I will put 10 kilonewton. Okay. And then axial also I'll put minus 10. Minus 10 means it will take us a compressive.
Yeah.
10 kilonewton. 10 kilonewton means roughly 1 metric ton. I applied it. I'm going to keep it. Okay. So what I would do is, for simplicity, instead of making this joint as a 5.6 meter, we will make this joint as 10 meter. Okay. Just for calculation easily we can find it out how it works like that. Okay. So we will save it. Now what we have done, we have applied the load also. Okay. Now we need to go to and add the analysis options. Analysis option, what we are going to do, working units metric ton code check. I will ask APRP to a 22nd edition. We will put it,
Yeah.
and then stress checks for number of divisions. At least three sections it should create. There is no not segmented here. Everything is same member sections, not a segment members. I put that one also. I'll update it. Greater than, less than. So two cross sections it will take. So now I added the code check option, and loading also I added it. That's it. Now what we will do, we will go here. Where is the tuber member? And we can check the values in the data generator. Also right click on the data generator. We'll check it what we have done. We have defined this options card. And if you want to report also, we can take all the reports. Joint deflection report, if you want, we can take yes. Member detail report, if you want, we can take all elements. Member end force also, if you want, we can take joint reactions. Stress at maximum unity check, internal loads. Double click if you do it, it will give yes, then we can take that one. We can ask it to print it out. Plate cell, there is no plate cell. Member UC report we need. So we'll take yes. Number of sections we already given. Unity check range report also we can take it. This only one member, so
Yeah.
it's not a problem. If it is many members, it will give in range also. So we will take all this print out, and the tubular sections what we are given, diameter, thickness, length smallness, yield stress, all these value it is coming here. And this is the member first joint, second joint connecting group label. No offset and all. I will tell you what it is mean by offset. And joints, two joints we are given. First joint we are given as a fixed boundary condition. Joint fixed is fixed one. And load we have applied one axial load on one
10. Yeah.
vertical z load. Okay. So when we apply this member, we have applied a load like this, right? So
Yeah.
what would happen? This will make a bending. So this is the fixed end, right? At this fixed end, this is the y axis. What is this? Is Z axis. This is the
Mhm.
x axis along the direction. So this would call moment. This is the bending moment, My. So this bending moment it would vary like this. This is the starting point 0. This is the 10-meter length. So this is 10 kilonewton force. 10-meter length is there. So it would come, the moment would come like this, linearly varying
Yeah.
it, right? So here at this moment, 100 kilonewton meter. That's the bending moment, maximum bending moment at this cross section. And because of this force at 10 kilonewton, we will be getting the shear resisting shear F is at resisting shear also same 10 kilonewton to come. Then there is one axial force also we applied like this 10 kilonewton. So there is one axial reaction also it will come. Fx equal to minus 10. We have put compression like this. So it would be
Yeah.
opposite direction reaction. So these are the forces it would come. One axial force, one vertical. If you see the shear diagram also, the 10 kilometer force is coming. The
Then yeah,
constant
it
shear it
will
will come.
come.
This is the shear force diagram.
Mhm.
This is the bending moment diagram. Axial loading also it would be throughout. It will be same 10 kilometer only. It will come.
Mhm.
So three forces are there. We will see how it is going to analyze this one. Okay,
Mhm.
whether this member is safe or not, we will see it. Then if you go to the analysis generator, you will take static analysis, basic static analysis, and this library section are okay. We will select the model here, open, then save it, then make a run. Simple run only. So it is running. So it run is over. So we go to this PostgreSQL database. This is the member. So if you go to display labeling, if you want to see the maximum unity check, it will show 0.06 it's coming. So we can see all these even if you want to see the moment diagram, you can see here this member apply. You see the moment diagram
Yeah.
0 to 100, and you see the shear diagram 10 kilonewton, 10 kilonewton. Okay, so this is it comes okay, what we expected. And if you go to this member review member, and it is showing Euler stress 440 actual. This is the FA. FA means axial stress. This is the actual axial stress 0.21, and allowable is 169. Allowable bending it's 15. It's coming because F by bending is the right 100 divided by 6 and modulus. If you see it, it will come. If you see the report, it would give the report also. Go to the report. Here also you can see all these moment of inertia,
Mhm.
6 and modulus, all these value, axial area, shear area. You see shear area, how much it is? 233.25. What is axial area? 466. So it's 50% it's coming, you see.
Mhm.
You understand?
Yeah. 0.5.
Yeah. Axial area is 466. Shear area is 233. Okay. And then see the allowable stress on the. This is the moment minus 100. This is the axial force. Then this is the joint reaction forces. Joint reactions. Joint displacement also. You see the displacement also. You can see it. Vertical displacement. You know PL Q by 3A, right? The cantilever displacement. You see here this one, if you force is applied here, the displacement it would be looking like this. This value is what is the value?
P.
Maximum display
Mhm.
P L cube divided by 3 EI, right? So if you substitute all these value, we know P 10 kilonewton, L also we know that's 10 meter. 3 we know, E is Young's modulus we know, I also section moment
Inertia.
of inertia that also we know.
Mhm.
If you substitute it, we can get this value
And there is
0.8
allowable for
forces.
this one, right? It's 200 over L.
Yeah, yeah.
For the cantilever, I think.
Yeah, for cantilever, we
Yeah.
have different allowable stresses.
Ah,
Allowable deflection value.
yeah.
Correct. And if you see here, what is the member detail report force, moment, axial stress? Axial stress is nothing but what is the total force divided by cross sectional area. You know the total axial stress is minus 10 kilonewton.
Yeah.
Minus 10 divided by what is the cross sectional area we have seen right here, cross sectional area 466, right?
Mhm.
So we can get this value, axial stress, actual axial stress, 0.21 it's coming. That is nothing but minus 10 divided by
The
cross sectional
area,
area.
yeah.
Yeah. Bending stress is M divided by section modulus. You can get this one. Moment
Yeah.
of inertia divided by Y value also you have to put. This is the applied axial stress, applied bending stress. This is the shear stress. Shear stress, you know what is the force? 10 kilonewton is the force. Shear area we know. We have seen
Yeah.
already here.
233.
Yeah, here we have seen, right?
I have the area. 0.5, I think.
Here you see the
Yeah.
0.5 A, V divided by 0.5 A.
Yeah.
That's the maximum shear stress.
Why it's zero point 0.5? Because we divide the member to uh, what you call it, two area, one for the bending, one for the shear.
No, 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 no,
That's
no.
why we are putting zero point 0.5 to
No, no,
get the
no.
maximum.
No, no, no. Usually the cross sectional area, if you see, if IB mandal, what we will take? We will take the
Ah,
for
okay. It will
calculation.
be
We will take the
in the
web
middle.
only, right? Web
Ah,
only.
okay,
The
okay.
web only. It's taking the most shear load, right? So
Yeah.
here tubular also it will take 50% of the area only the uh, shear load.
Ah, okay, okay, okay. I guess
That
it.
from the strength of materials we can
Mhm.
derive it by only the shear area we are taking. Okay, and then this member internal load summary. Okay, yeah, you can get all this value, actual bending and slurness ratio K